All right, welcome to day 8. Today's topic is intersection of two polar curves and also finding the area bound between two polar curves. First one for the homework, you wanted one petal of this. So over on the right there, set it equal to 0 and solve. You get 3 theta is pi over 2. So we want to think of pi over 2 and negative pi over 2. Remember, it's helpful to think about where you would be at 0. When you put 0 into 2 cos 3 theta, you get back 2. So that tells us that that's our 0 point right there. So that's why we want to do one positive, one negative on either side of it to get the full petal. So that's why we know we have negative pi over 6 to pi over 6. Square everything, do your power reduction, sub in, you get pi over 3. So for this one petal, when you put in 0, you get back 0. So one of our petals should start at 0. So setting our equation equal to a radius of 0, divide by 6. So we're looking for places where sine is 0. So 0, pi, 2 pi. So set 2 theta equal to 0 and pi. You get pi, theta equals 0 and theta equals pi over 2. Square everything, do power reduction, sub everything in, and you get 9 pi over 2. Note for these last two, they just wanted one petal. If they wanted the whole thing, in that first one we would have had to multiply by 3, and in this one we would have had to multiply by 4. All right, so to think about what your integral bounds would be, start out, think about 0, sine 0 is 0, so 1, so this is our 0 point. Sine pi over 2 is 1, so here's going to be pi over 2. Sine of pi is negative 1. Sorry, sine of pi is 0, so we get back 1. Sine of 3 pi over 2 is negative 1, so that gives us 2, and then that would bring us back. So we've got a full 2 pi. Remember, you always could just trace that on a graph if you were more comfortable with that. We got 1/2 our radius squared d theta, FOIL it out, do your power reduction, sub everything in, and we get 3 pi over 2. Now for this next one, it's the same equation that we just had, but we only want above the polar axis. The polar axis is essentially our x-axis. So here we finished after pi. So we want to do this same one, just 0 to pi. Now I just put dot, 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 because it would be the same foiling out, doing power reduction and everything of what we just did. Sub everything in, and we should get 3 pi over 4 minus 2. For this one here, they just wanted the inner loop. So again, I think it's helpful to think about where are you at 0. Cos of 0 is 1, so you get back 3. So here's 0. Pi over 2, cos of pi over 2 is 0, so you get 1, so there's pi over 2. And then cos of pi is negative 1, so you get back to 1. So that's pi over there. So the loop has already started after pi. So I just like to do that just to kind of get a sense of what's going on. So we know our inner loop, the bound should be on either side of pi. So just set that equal to 0, subtract the 1, divide by 2. Cos is negative in the second and fourth quadrants. If you've got a cos is negative 1/2, you've got a 60-degree reference angle. So that's really 120 and 240 we're looking for, which is 2 pi over 3 and 4 pi over 3. FOIL it out, do your power reduction, sub everything in, and you get pi minus 3 radical 3 over 2. All right, for this one, we know our inner loop goes from 2 pi to 4 over 3 to 4 pi over 3, so that's this here. So then the outer loop, because we want it to be continuous, we want to go from negative 2 pi over 3, because that's the same as 4 pi over 3, all the way to 2 pi over 3. So we want to go like that. So start from negative 2 pi over 3 around. You also could have hypothetically have gone from 4 pi over 3 to 8 pi over 3, and that would have worked as well for that front one. Now, the foiling out, the power reduction stuff is all the same as before. And I actually worked it out, but the part we're subtracting is just the answer from the previous problem, so you could have reused that if you wanted. The other one, we would have some different stuff to sub in, but eventually you get pi plus 3 radical 3. And the calendar problem, you put in 0 for sine, you get back 0, so we're starting right here. Pi over 2, you get back 3. So there's pi over 2, and then pi, you're back to 0. So this complete loop is done in just pi, so we want to go from 0 to pi. Square it, you can pull the 9 out, do your power reduction, sub everything in, you get 9 pi over 4. All right, so we're going to be on the day 8 notes in the notes packet. So first thing we want to do is we're going to find the intersection of two polar curves. So let's set them equal to each other. So we'll have cos of theta equals 2 radical 3 minus 3 cos theta. We can add the 3 cos theta over, giving us 4 cos theta equals 2 radical 3. Divide by 4, and we'll get cos theta is equal to square root of 3 over 2. Well, cos is positive in quadrants 1 and 4. If we've got adjacent is square root of 3 and hypotenuse is 2, meaning opposites 1, that means we've got a 30-degree reference angle in each of these. 30-degree reference angle means we're working with pi over 6. So in the first quadrant, we have pi over 6. If you've got a pi over 6 in the fourth quadrant, that's 2 pi minus pi over 6, so 11 pi over 6. Now they wanted the points of intersection, so our answers are going to be pi over 6, comma, whatever we get back, and, sorry, other way around. Whatever we get back, comma, pi over 6, because it's r comma theta, and then whatever we get back, comma, 11 pi over 6. So sub into whichever one you think is easier. Probably the cos is easier. And you're just doing the cosine of that reference triangle, which is just square root of 3 over 2. So we get radical 3 over 2 for our radius, comma, pi over 6, or comma, 11 pi over 6. All right, same thing for the next one. Let's find the points of intersection. We'll set these equal to each other. Add your 2 sine theta over. We'll have negative 4 sine theta equals 2. Divide your negative 4 over, and you'll get sine theta equals negative 1/2. Sine is negative in the third and fourth quadrants. We're working with a 30-degree reference angle because our opposite is 1. So that's a pi over 6 in each of those quadrants. So pi plus pi over 6 will give us 7 pi over 6 for one of them. The other one we know from the last problem is 11 pi over 6. And the easier one to sub into is probably the bottom one. It's just 6 times what or negative 6 times what the sine was. Well, sine was negative 1/2 times negative 6, so that'll give us 3 for each of those. Now, if you look at the graph, it's clearly intersecting at 3 points, but we only got 2 answers. We got this one and this one here. So the other spot this is intersecting is the pole. Now, at the pole, your radius could be 0 for lots of different possible values of theta. So it might not be there at the same time, which is why we didn't get the solution here. So what you can do, you could graph it and just visually look and see that it crosses at the pole. Or you could take them individually and see if they're both radii are 0 at some point. They don't have to be at the same point, but just at some point. So if you set 0 equal to 2 minus 2 sine theta, you could add the 2 sine theta over, divide by 2, and you get 1. And sine theta is equal to 1 at pi over 2. So we are going to hit the pole when theta is pi over 2 in the first one. In the other one, sine theta, oops, we want to make this be 0. Sine theta is 0 first at 0. And again at pi and 2 pi. So notice the radius is 0 in both of them, but not at the same angle measure, not at the same value of theta. So as long as you get that they have a radius of 0 at some point, we know they're going to cross, but since it's not at the same value of theta, we can't write it as a point. So all you say is the pole. So we've got those 2 points where they're crossing at the same radius and the same value of theta, but because at the pole, it's a radius of 0 with lots of different possible values of theta, as long as you get that though each equation has a radius of 0 at some point, then you can say it is the pole. If one had it at some point and the other didn't, then it wouldn't be one of our intersections. And again, you can either look at that graphically or check them separately by setting them equal to 0. All right, next we want to find the area that's bound by 2 polar curves. So first off, we need to think about when we found the area inside a polar curve. Really, what we were finding is it was like all these like wedges, these radii that were coming out, and we found the area of those. Because if we want to find the area that's between this green polar curve and this red polar curve, we want to imagine a dotted line going down the middle like we have there. Before the dotted line is graph that is plotted from the 4 sine theta one. So that area is going to be the area for the 4 sine theta from some starting value of theta to some finishing value of theta. And then it switches over to area from the red one. Again, because our area we define as coming from the pole. It's not a top minus bottom like we had when we had just regular functions. So it's coming from the pole, and that's why we have to split it like that. So you see it broken down a little bit to the right there. So we're going to do the red section there plus the green section. Well, a couple things we need to know. We need to know, first off, when do they intersect? So let's set them equal to each other. If we add the 2 sine theta over, we get 6 sine theta equals 2. If we divide by 6, we'll get sine theta equals 1/3. And then theta would equal arc sine of 3, or arc sine of 1/3, sorry. Well, that's where they're crossing. So that's representing this spot here. So that should be here in this picture. So it's when our green one's finishing. So this is our arc sine of 1/3. And it's where the red one's starting. So this is also arc sine of 1/3. But we need to think about, where does the green one start? Well, the green one is starting at the pole. So let's take the green function, set it equal to 0, and it'll tell us the value of theta when it's at the pole. Well, if you divide by 4, you get 0 sine theta. Sine is 0 when theta is 0. So our green section, we're going to be going from 0 to arc sine of 1/3. For the red section, we've got to see when is it going to be at the pole. So if we do 0 equals 2 minus 2 sine theta, add your 2 sine theta over, divide by 2, and you get sine theta is 1. Well, sine is 1 when theta is pi over 2. So that means the red one, we're starting at arc sine of third, and we're finishing at pi over 2. So to figure out our area that is enclosed there, we're just going to add our 2 integrals. Now, because we have 2 of those sections, we'll just end up doubling it. So we're going to do 2 times. We'll do our red one, which is going to go from arc sine of a third to pi over 2. And our red one, we had 2 minus 2 sine theta, d theta. And then plus, we've got our green one that's going from 0 to arc sine of a third. And that one was 4 sine theta, d theta. Now, a lot of these are going to be not terribly difficult to do by hand. The arc sine 1/3 makes this one a little bit more challenging. So because of that, we're going to let you put this one in your calculator. So if you could pause the video, take a moment to put this in your calculator. Make sure you are in radian mode. Don't forget to put the ×2 out front. And we're going to 3 decimal places, our normal AP rounding standard. So go ahead, pause the video right now to take a second to punch that in. And to 3 decimal places, we should have got 0.676. Now, most of the ones on your homework, you've got to do an exact form. They'll be more manageable because you won't have the arc sine of a third that you'd have to sub in. And the next one we do, we'll show you working it all the way through in exact form. So if we go to the next page, we want to find the area that's inside our red one, but outside our green one. So what we're going to do is we're going to take basically a quarter of the red one and subtract off that little hump from the green one. And then we'll double it because there's 2 of those sections. Because in the end, what we want is we want all of this space, essentially. Well, we've got to figure out what our bounds are for that. So for the red one, it's just r equals 2. So the theta values, it's going to be 2 no matter the value of theta. So this is starting at theta equals 0 and finishing at theta equals pi over 2. So nothing too fancy about that one. So for 2 minus 2 sine theta, if you put in 0, you'll get 2 minus 2 times sine of 0. So that's starting here. So theta equals 0. If you put in pi over 2, you'll get 0. So that's this one here. So this one is also going from 0 to pi over 2. Okay, won't always necessarily be the same, but in this case it was. So we are going to have, we've got to make sure to double it again because we've got 2 of the sections. We're going to have the integral from 0 to pi over 2. We'll have 1/2. I think we forgot our 1/2s on the last one. Let's go back to that. And we forgot our squareds. So we're going to have 2 parts, so we've got to double it. First we'll have our red part. So our area between polar curves will have 1/2. We're going to be doing the integral Again, the red part's going from pi over 2, or sorry, from the arc sine of 1/3 to the pi over 2. Then we've got our radius squared d theta. In this case, our radius was 2 minus 2 sine theta. Then plus, we got to do the same idea for the green one. So we've got a half. This one we went from 0 to the arc sine of 1/3. And then we'll do our radius squared. So 4 sine theta parentheses squared d theta. And what we're going to do is we'll give you a couple seconds. Go ahead and pause the video. Type this in. Because the arc sine 1/3 makes it kind of challenging, so we're just going to do this one in the calculator. It's about half and half on the AP. Sometimes they have you sub it in the calculator. Sometimes you have to do it exact. Most of the ones on your homework, I'm going to have you do it all the way out exact. But because of the arc sine 1/3 here, go ahead, pause the video, punch this in the calculator, see what you get, and make sure to keep it out to 3 places. All right, so we should have gotten 0.676 for that. So moving on to our next page in the notes, we now want inside that red one, but outside the green one. So that would be this space here that we're going to look for. And what we're going to do is we're going to just do like the first quadrant part and double it, kind of like what we did on the last one. So what we're going to have to do is basically like the red quarter circle minus the green part. Well, because there's nothing fancy going on for the red, it's just starting at 0 and going to pi over 2. So we'll have 0 to pi over 2 for the red part. And then for the green part, if you put in 0 to that, we get back 2. If you put in pi over 2, we get back 0. So that also happens to be going from 0 to pi over 2. Won't always be the same, but in this case, it was. So we're going to do the quarter circle part minus the little hump there, and we're going to double the whole thing. So we're going to have 2 times 1/2 the integral from 0 to pi over 2. We'll do our green part, which was just r equals 2 squared and then d theta, minus 1/2 integral from 0 to pi over 2. We'll do our other radius squared, the 2 minus 2 sine theta squared d theta. So if you pull the 1/2s all out, they basically wipe out the 2. So we're just going to have integral from 0 to pi over 2 of 4 d theta for this one. I'm going to multiply this out off to the side so we don't have to keep rewriting the integral as much. We'll have 4 minus 8 sine theta plus 4 sine squared theta. Well, that's going to be 4 minus 8 sine theta plus 4, and then we got to do our power reduction. So we're going to have 1/2 minus 1/2 cos of 2 theta. If we distribute the 4 through, we'll have 4 minus 8 sine theta plus 2 minus 2 cos 2 theta. Remember, we got rid of the half because we pulled it out and it wiped out with the 2. So now we have minus 0 to pi over 2. If we combine our like terms, we'll have 6 minus 8 sine theta minus 2 cos 2 theta d theta. And again, keep in mind, we pulled out the half and wiped out the doubling that we were doing. So here we'll just have 4 theta going from 0 to pi over 2. Minus, we're going to have 6 theta plus 8 cos theta. We'll have a sign here, but we got to do a correction by multiplying by a half. So we're going to just have minus sine 2 theta. and we're going from 0 to pi over 2. When we sub in pi over 2 times 4 will just give us 2 pi. Minus the 0. And minus start a parenthesis. If we sub in pi over 2, we'll get 6 pi over 2, which is just 3 pi. Cos of pi over 2 is just 0. 2 times pi over 2 gives you pi. Sine of pi is 0. Minus, start a parenthesis. When you put in 0, we'll get 0. Cos of 0 is 1, so we'll get 8. Sine of 2 times 0 is just 0. So distributing our negative, we get 2 pi. This is going to give us a minus 8 pi. But then this negative, when it distributes, will give us minus 3 pi back to a plus 8 pi. So we'll have minus, or sorry, not 8 pi, just plus 8. Then we'll have minus pi plus 8 for our final area that is between those two polar curves. So this would be an example of how you would do it all the way out in exact form, and that's the kind of thing that you're going to do on a lot of your homework ones. Have a great rest of your day. And you got your homework assignment to work on still for tonight.